There are many different flow control devices designed to improve a car's aerodynamics, but pretty much all of them are designed for when there is no crosswind. For example, front wheel spoilers are great in that they can reduce a car's drag, sometimes even by 5%, but they're optimized for head-on winds. Today we're looking at a flow control device that might improve a car's aerodynamics when there is a crosswind, which also includes when a car is cornering. We can see this type of device in figure 1, so these side spoilers they're labeled. And we have a spoiler at the front of the car labeled here as the front bumper spoiler, then one on the A-pillar which is called the quarter glass spoiler. And to see what effects these devices have on a car's aerodynamics when yawed, so when there's a crosswind hitting the car, we're looking at this paper called, if we scroll up here, Influence of Side Spoilers on the Aerodynamic Properties of a Sports Car. It's open access, so you can find it in the link below, and the DOI should be at the end of the page for those interested. Here we go, just there. So what are these side spoiler things doing? How should they work? And what's the thinking behind why they might improve a car's aerodynamics in a crosswind? Well, when a car hits a crosswind, it experiences a side force. The side force can make a car turn outwards, which reduces its stability. The thinking behind these flow control devices is that when in a crosswind, you can open them up by rotating them out, as we can see in figure 1 with these different colors that corresponds to different opening amounts. And then you can have these surfaces sticking into the flow. You then get high pressure in front of the spoiler and low pressure behind it, so overall you generate a force. This force is located some distance away from the center of the car, so you produce a moment. And hopefully that moment is enough to correct the car's heading to help turn into the crosswind. On the other hand, if you prefer, you could always use these spoilers to help you turn where that side that you're turning into, you deploy them and that produces a moment to help you turn into the corner. So depending on what your needs are, you can use these spoilers very differently to help you. That's the idea at least. Let's discuss these spoilers' locations and operations a little more because they're quite unusual. So first of all, let's look at this A-pillar, so this quarter glass spoiler thing. So the spoiler spans pretty much the entire length of this A-pillar, and the authors note that this spoiler's geometry and the front bumper spoiler's geometry weren't optimized, they were just simply made to fill this gap and the length as much as possible. So their geometry could probably be optimized to improve their performance, but we'll see later what their general performance is anyway. So the A-pillar spoiler, also known as the quarter glass spoiler, rotates and sticks into the air. They can then change how much it rotates out and hence how much it sticks into the air. The front bumper spoiler, so the one down at the front corner of the car, around the bumper, is hinged at the back, so it folds out more and more. It is also curved so that it can just hug the front of the bumper perfectly when it's stowed, and that would probably reduce the drag too. And then from there, you can rotate it out, and it's also kind of more like a scoop then that catches the air. Now, one thing that really struck me when I first saw this particular bumper design is that it's extremely like an extreme canard. It's looks like a really big canard that just folds out. And the reason why is because you can see that it is kind of angled so that the air will shoot over the top of it. As such, there might be some downforce produced by it, and I expect there to be some separation behind it too. So the downforce will be lessened, but I think that this front bumper spoiler should produce downforce, albeit inefficiently. And the quarter glass spoiler probably will produce some downforce too, but it really doesn't look like any other flow control device that we commonly use. So that's the general idea of these geometries. Let's now jump into their method. So they used CFD to find out what the effects of these spoilers were on the car's aerodynamics, which is nice because we'll get to see a lot of information. And they used Ansys Fluent, which is one of the top CFD softwares. It is also quite expensive. Another top CFD software, but free, is OpenFOAM. And if you want to learn OpenFOAM, then check out our courses here. Now in figure 2, we see their domain and mesh. And one thing I'm not too sure about is the inlet shape for their domain. So in figure 2a, you can see that on the left, that flat face is the inlet. And then under regular heading conditions, so if you just have a head-on wind, that inlet is completely fine, that shape. But because we have a yaw angle to the flow is now coming in at an angle to the inlet too. With this particular shape geometry where we have a 90-degree corner at the front left edge, if you see this corner here, if you had a generic left wall, side would just be a generic wall, you'd get flow separation around that point because the flow is going into the regular inlet and then it bends around that corner and separates there. So to stop that from happening, the authors made the left wall an inlet too. An alternative way to solve this problem would be to make the inlet curved, so as you would have like on an airfoil at different angles of attack. And still another way to correct this potential problem would be to yaw the car so that the inlet flow is still straight, and the sides can then be regular walls, but then the car still sees a crosswind because it is at an angle to the inlet, but then you could only test it at one angle because you'd only have one mesh. If you wanted to test the car at different angles, you then have to yaw the car more and remesh. So there are three general different ways that you could solve this problem of having the flow coming around this corner and having a yaw angle. And the approach that we have here is one way to solve that problem. So in figure 2, we see their mesh and they used TET elements. That's especially important for this CFD because even the inlet flow isn't going straight. So by having an unstructured mesh here, you can better capture the flow and not be biased towards one direction. For example, if you had a structured mesh and you used hexahedral elements, for example, so little cubes or rectangular prisms all over, they are far better suited to flows that are just straight. That's because the faces of them are perpendicular to the flow. As such, the assumptions you make with the CFD equations, namely the small angle trigonometry assumption, is more accurate when you have that particular setup. But once you start having flows that are non-perpendicular angles to these faces, those assumptions become more and more erroneous and can even change the results quite dramatically and even lead to divergence in the extreme case. So using a TET mesh here is very good. And just as a general rule, whenever you're expecting for there to be a wake, so that's when you have a bluff body or a streamlined body that is stalled, you should use an unstructured mesh because it will give you more accurate results. When you have a streamlined body with attached flow, so the wake will be very small, a structured mesh is generally more accurate. Let's move on to the mesh independence test now. So in table 1, we see how changing the number of cells changed the drag, side force, and lift coefficients, just in this table here. And note that this simulation was done with RANDs, and the Terminus model was the K-Omega SST, which is really good. So the Y plus value was 30, which is a little high, but still within acceptable limits for this turbulence model. And in table 1, we see that they tested meshes from 22 million cells up to 44 million cells, which is really good because that is a very large range that they tested over. And the coarser mesh gave very different results across the board compared to the two finer meshes. The two finer meshes gave results consistently within about 1% of each other, so that's really good. So you might see this drag coefficient and think that that's a really high value as well, generally speaking, 0.38. And it is a high value, but that is also for a yaw angle of 15 degrees, so that is why it's also so high. We'll see later on how this yaw angle changed these various coefficients, and we'll see values that are even higher than this potentially. Now, from this mesh independence test, the authors concluded that they could use 33 million cells, which is fine. Now, we don't have a validation study, which isn't great, so I guess from here, we should really just look at the trends and general flow features. Let's now jump into the results. So in figure 3 here, we see the results when they are changing the quarter glass spoiler angle. They tested 6 different angles from 0 degrees, then 27.5, 55, 82.5, 110, and 137.5 degrees. So that means that this little flap was at different angles going along. And it's a little hard to tell, but the 90-degree angle would be when the flap is literally just extended completely sideways and is flat to the oncoming flow, it's perpendicular. And then when you go above 90 degrees, the flap is actually rotating more in towards the windshield, and that's reducing the projected frontal area. So the 90-degree case gives the greatest projected frontal area, but how does changing the angle affect the moments and coefficient and the forces? So one thing I should mention is that I'm pretty sure this is for a crosswind of 15 degrees, at least that's what I can tell. And in figure 4, we see in the top row the force coefficients on the spoiler in the left figure, and then on the total car on the right figure. That's an important distinction to make because you might get more force on the spoiler, but the car's aerodynamics might change for the better and the overall force might drop, or it might increase even more. Also, the blue line is the drag coefficient, which is labeled CX. The side force coefficient is CY, and that is red, and the lift coefficient is green, and that is labeled CZ. That's something to note that sometimes instead of saying the drag, side force, and lift coefficients, these symbols, the CX, CY, and CZ are given, and that is just literally the coefficient in the X, Y, and Z directions. In the bottom row, we see the moment coefficients on the spoiler in the left, and then on the entire car on the right. And similarly, these labels are given as CMX, CMY, and CMZ. And that is just for the moments about the X, Y, and Z axes, the coefficients. So the rolling moment coefficient, the pitching moment coefficient, and the yawing moment coefficient, respectively. In the top left figure, so the force coefficients on just the spoiler, the drag coefficient increases for all quarter glass spoiler angles. So it doesn't matter what you put this spoiler at, what angle you put it at, it's protruded into the flow, and it creates more drag. Not only the drag, but also the drag coefficient. And that's kind of expected because as you hit about 90 degrees, the drag coefficient reduces from there as it folds back in more and more. As for the side force, it initially increases before decreasing at higher angles of attack, or higher deployment angles. So in figure 3, we see the pressure coefficient contours over the car and spoiler, and maybe at lower deployment angles, the flow gets in underneath and creates higher pressure on the back face, which helps produce a positive side force. I don't know, we can't see the other side of the spoiler. But then as the spoiler flips out more and more on the side force, perhaps the side force on the spoiler reduces more and more. As for the lift, actually all deployment angles produce more downforce, and the best case scenario is 80 degrees, which is kind of logical when you think about it, because that is when it is most angled to make downforce. One thing that I'm a little surprised at is that at 137.5 degrees, so it's still angled out quite a lot, there's almost no downforce, so this green line is hitting the x-axis. Anyway, that is for the forces just on the spoiler. What about how the forces change on the entire car? So we see those results in the right figure. So again, any deployment angle comes with a higher drag, that's expected. And then we see in figure 5, down here, we see some cut planes going through the spoiler, and we see some streamlines too. And it's quite clear that as the spoiler is deployed more and more, so we go down these columns, we get a bigger wake and a greater vortex rolling up over the spoiler. So in the right figures here, you can see this vortex rolling up, and that vortex is effectively a wingtip vortex, so that's induced drag. So there are two reasons for more drag production here. The spoiler creates a more pressure drag because of the larger wake that it produces when it's flipped out more, and then it produces more induced drag because of that vortex production, which is probably because it's producing more downforce too. As for the side force, in figure 4b, if we scroll back up, this top right figure here, we see the same trend for the entire car as we saw for just the spoiler, namely at that 27.5 degrees, it actually increases before decreasing. The downforce is a little interesting in that, okay, as expected, we get downforce from the spoiler, but that downforce is maintained at greater spoiler deployment angles too, whereas we saw that for just the spoiler, when that deployment angle rotated past 90 degrees, it trended back to 0 again. And it kind of makes sense why for the entire car we don't lose all that downforce as the spoiler is rotated more, and that is because, as we can see in figure 5 again, as the angle increases, so as we go down these columns, it still disturbs the flow over the car almost just as much. The streamlines show how the flow really still blows out too. So the entire car's downforce isn't as sensitive to the spoiler's angle once it passes 90 degrees as the spoiler itself. So from those graphs, we can conclude that the quarter glass spoiler is bad for drag, good for downforce, and likely good for sideways force because it helps you overcome the wind's tendency to push you away. As for the moments, let's look at the car's moments in figure 4D because the moment on the spoiler isn't really important other than making sure that the mounting mechanism can handle the moments. So in figure 4D, we see that with the spoiler deployed, so we see the total moment coefficient, so the moment coefficients on the entire car. The CMX value, which is the yawing moment, is positive. The authors say that that means that the car is yawing into the wind more. So that's good. That means that the spoiler is correcting your direction and pointing you into the wind more. That's what we want to achieve. As for the pitching moment, so the CMY value, it is positive, but that doesn't really change much. I think that any changes here are probably within a CFD error. But still there's a positive pitching moment, which means that the car wants to tilt up and pop its nose up more. So from this graph here, we can see that the quarter glass spoiler does help point you into the wind and overcome the wind's potential tendency to point you away. So that would also be good for cornering too. Now let's move on to figure 7 because we see this like gray fog thing. I'll show you once we get down there. Here we go. So this like gray fog bit. That's the isosurface of where the total pressure equals 0, and that is for the spoiler deployed at 110 degrees. So in effect, this is showing you where the wake is. This is where we have an energy deficit. Sorry. So we can see this stream coming off the spoiler, and that is the vortex and the wake associated with it. So that is with the quarter glass spoiler only deployed. How does the front bumper spoiler fare? So in figure 8, we see some surface pressure contours for when it's deployed at different angles. And again, it looks a lot like a massive canard. As expected, as it unfolds more and more, there is a larger surface area exposed to very high pressure, which it should come with a lot of drag too, I think. And probably downforce too. In figure 9, that confirms what we saw, where in the top row, that for both the spoiler's drag coefficient, so Cx, and the total car's drag coefficient, we see the drag coefficient increasing with increasing deployment angle too. There's really only one instance where it actually has a lower value, and that is on the left graph. So this blue line here, when it's about 25 degree deployment angle, the drag is a little bit lower. But looking at figure 8, that corresponds to the middle figure in the top row. I guess that kind of makes sense because you can see that there's some lower pressure on the outside, so there's some green here, which might create a bit of thrust. So perhaps you could reduce the drag of the spoiler in this configuration, or it might just be error in the CFD. Anyway, in figure 9, we still see that the Aero car's drag coefficient increases quite a lot too. So anyway, as for the downforce, so the green line across the board, increasing the front bumper spoiler deployment angle increases the downforce more and more. So it's effectively a very large canard, as we suspected. The side force is also good, with pretty much every angle producing both some in the spoiler and the overall car as well. And then in terms of the moments, so the bottom row, we get higher yawing moments, so the green line, and that is also good because the car will be yawed into the wind and straightened up a little too. So we can conclude from these figures that the front bumper spoiler is good in terms of downforce production and a restorative yawing moment, but bad for drag, as you'd expect by poking out such a large plate into the flow anyway. So we can see in figure 10, if we scroll down here, how it creates a larger and larger wake as it's rotated more into the flow. Although I should say that this is for a wheel that is completely covered. So if you have a more open rim, then these results might change a little, in particular because the drag penalty might not be so bad, because in figure 10, if we see in the top left, the wake is pretty much nothing for when the spoiler is closed, but for a regular car with even a moderately open rim, there will be some wake around this region here. So perhaps the negative effect of the spoiler won't be as bad because the wake will be larger without it anyway. So those are the results for just one yaw angle, 15 degrees. What happens at different yaw angles? So in figure 12, we see 3 different car configurations. It's a little hard to see, but effectively the left one is for the quarter glass spoiler deployed at 110 degrees and the front bumper spoiler at 50 degrees. Then the middle configuration is without these spoilers, but there is still a trunk spoiler. And then the rightmost case is with even this spoiler at the back removed. So they also tested with 2 more configurations that they don't show here, which are one just with a quarter glass spoiler and one just with a front bumper spoiler. And in table 2, we see the various force and moment coefficients for all these configurations at 0 degrees, for 0 degree yaw, sorry. Interestingly, the numbers say that the base case, which is with the car just with the trunk spoiler, had the lowest drag coefficient, so it was 0.333. And that's even lower than the base car, which didn't have even the trunk spoiler. However, this difference is just 6 counts and likely within the CFD error, so I don't know if that's actually the case. As for the 2 spoilers at the front of the car, both increased the drag, but surprisingly, the front bumper one didn't do too much, about 10%, whereas compared to the quarter glass spoiler, that increased the drag coefficient by about 35%. And when you combine them together, that number just increases even more, so that combined value goes up to 0.492. In fact, the front bumper spoiler by itself doesn't increase the drag coefficient as much as when you put it with the quarter glass spoiler. So when you put them together, there's a synergistic effect which makes them worse than the sum of their parts. But again, these minor differences might be within the error of the simulation. We're not too sure. But anyway, that's still quite interesting. In terms of the side force coefficient, we see similar patterns where there's negligible difference between the regular car with and without the trunk spoiler. Then both the quarter glass and the front bumper spoilers reduce it, and the front bumper isn't as effective as the quarter glass spoiler. But then there's a synergistic effect where they're way more effective together than the sum of their parts, and in this case, it's potentially good. So maybe they're interacting with each other. We'll have to see later on if that's the case. Then for the lift coefficient, the trunk spoiler really makes a huge difference by producing a lot of downforce. So this middle column here. But surprisingly, the quarter glass spoiler is even better, producing 200 counts of downforce compared to 145 for the trunk spoiler. The front bumper is pretty good too, and as you'd expect for the yawing moment, so the CMZ value, the rightmost column, the spoilers are producing yaw moments, but the front bumper spoiler is more effective. So in terms of efficiency, the front bumper spoiler is better because it produces more yawing moment here, but with less drag penalty. Let's now go to figure 13 to see how the two spoilers are interacting with each other. So the leftmost figure is just the front bumper spoiler, and the flow gets redirected up over it, and that's pretty good. That's like a canard, as you'd expect. It goes over the front wheelhouse, so that could be good. Then the middle figure is for just the quarter glass spoiler deployed, and that is shooting a lot of air over the top, and then it goes straight into the trunk. And as a result, we see higher pressure over the trunk, so we see more red in that region. That means more downforce is being produced there. So the quarter glass spoiler is actually increasing how much downforce the trunk spoiler is producing too. So there's a direct effect on the downforce, which is the downforce just coming from the quarter cord spoiler. Then there's more downforce in an indirect way, which is coming from the trunk spoiler too. And the rightmost figure is when you have both the front bumper and quarter glass spoilers deployed together. And here again, we get high pressure over the trunk spoiler, but we can also see how the flow shoots over the front bumper spoiler and then underneath the quarter glass spoiler, and then even straightens up and hits the trunk spoiler even better. There's even redder flow here. So not only are the front and quarter glass spoilers working well together, but they're also working well with the trunk spoiler. So all these three spoilers are working together in a very synergistic way. That's really rare because getting even two flow control devices to work well together is hard, and getting all three and locating them all over the car is really hard. So that's quite impressive. Let's now jump to figure 14, where we see the effects of different yaw angles on the car's performance. So one thing that stands out is that no matter really what force or moment coefficient you're looking at, the trends are always kind of the same regardless of the car's configuration. So really all that happens is just these lines mostly shift up or down, and that makes it easy to remember what happens. Now in terms of the drag coefficient, so the top left figure, we see that the car with both the front bumper and quarter glass spoilers, so the red line, has a higher drag coefficient across the board, but as the yaw angle increases, the drag penalty drops more and more. So we can say here that at higher yaw angles, which is when you'd want to have the car spoilers deployed, the drag penalty becomes less and close to nothing. In terms of the side force, so this middle figure here, the spoilers consistently drop it, so it helps it stop the car being blown away by the wind. So that's quite good. Then for the lift coefficient, so the bottom left figure here, the spoilers arguably don't increase the downforce at non-zero degree yaw angles. The blue line is just for the trunk spoiler, and the red line, which is for the two spoilers at the front, the downforce isn't really increasing much here. So while at 0 degrees, the two front spoilers greatly improve the car's downforce, and we saw in figure 13 how the three spoilers work together, once you start yawing the car, that benefit goes away. That's a little surprising, I guess. And I guess that's also because maybe the flow is being redirected differently over the spoilers now, so they can't work together as much. Anyway, in terms of yawing, the yawing moment, which is the bottom right figure here, we see that it increases. So that means that as the yaw angle increases, the restorative yawing moment increases too, which helps reduce how much the car is yawing away from the wind and yawing it into the wind even. So that's really good. And finally, in figure 15, we see the wakes of the various cars and yaw angles. It's down here a little bit. Here we go. So I just want to focus on the leftmost column because That is the car with all three yaw angles, and I want to see why the yaw angle increases when increasing from 0 degrees, the synergy between them vanishes. So the top figure is 0 degrees, and then as we go down the column, the yaw angle increases more and more. And we can see that the vortex from the quarter glass spoiler becomes far less cohesive, and that seems to reduce how much it gets flung into the trunk spoiler. And we can see that as the yaw angle increases, the red over the trunk becomes more orange and yellow, so the pressure drops as well, sorry. So in effect, that synergy that all three spoilers had at 0 degrees evaporates. And with that, we come to the end of this podcast. It was really cool to see how these very unique ideas and how combining them affected the flow, and particularly in this synergistic effect. So if you like this podcast, hit the like and subscribe buttons. And if you want to learn OpenFOAM, which is a really powerful CFD software, check out our courses in the link below. And we'll see you soon. Peace amigos.